Welcome back. This last section looks at relative motion. We'll quantify displacement, time and acceleration with respect to different observers. I'll make some important assumptions in this section, but I'll wait till the quiz to tell you what they are. Meanwhile, keep your ears and your mind open. In this clip, I'm walking at about 2 meters per second with respect to the train. I'm going to write WRT for with respect to. But the train is travelling at, say, 3 meters per second with respect to the ground. So what's my velocity with respect to the ground? Well, you know the answer. It's easy here because the two vectors are parallel. To save writing, I'll use this convention. V sub f is the velocity of the moving frame with respect to the ground. V dashed is the velocity of the object with respect to that frame, and v is the velocity of the object with respect to the ground. Here is the velocity of the train with respect to the ground, my velocity with respect to the train, plus my velocity with respect to the ground, v equals v sub f plus v dashed. But what if the two velocities are not parallel? What if a boat heads north across a river flowing to the west? Well, we don't have the budget for a river, so here's a dinosaur heading north across a small tectonic plate that's moving west. Time for you to revise some vector addition. Yes, you're right. Here our moving frame goes west, so v frame is west. The dinosaur walks north, so v dashed is north, and the resultant velocity of the dinosaur over the Earth is v equals vf plus v dashed, which is indeed northwest. Maybe that's why the dinosaurs went extinct. They walked over the edge of a tectonic plate. Here's another problem for you. What direction does the dinosaur head if she wants to go north over a plate travelling west? Draw a vector diagram and identify the vectors in the equation v equals vf plus v dashed. So yes, if the tectonic plate is going west, or if the current in the river is flowing west, then the sailboat and the dinosaur have to head east of north. So far, we've just looked at velocity. Now let's look at displacements observed in different frames. Here are my x and y axes fixed on the desk. And here is my moving frame of reference, also with axes. I'll call them x dashed and y dashed. So here is the displacement vector r dashed with respect to the dashed reference frame, the frame that can move about. And here is the displacement vector r in the fixed or undashed frame. The vector addition looks familiar, only here we write r equals rf plus r dashed. Now, to allow for velocities, we let all of the r's vary in time. Once again, we use Greek letter delta to mean the change in. So, delta r equals delta rf plus delta r dashed. Then we divide by the time for these changes, delta t. And if the time interval is small enough, this gives a measure of the velocities. Aha! That's a familiar equation, and now we've derived it. I mentioned some strong assumptions. Did you notice those? Let's discuss that in the quiz coming up, along with some other important consequences. With this week's work, you should be ready for the first experimental investigation. So get started on that. Don't leave it until the last minute. Next week, we'll be looking at motion in 2 or 3 dimensions, especially circular motion and motion under gravity. But first, there's the quiz and then the test for real marks. Don't panic about the test, but prepare for it well. Make sure you really understand the material in this presentation and in the quizzes. It really is worth looking at them again, pausing if and when you need to. And don't forget to use your pencil and paper. Good luck and see you next week.